Welcome to a new lecture in which we'll speak about advanced topics in the field of communication networks. So more specifically, we'll talk about interesting techniques, problems, mechanisms that you typically find in large-scale network infrastructures. So what do I mean by large-scale? Large-scale data centers, like the ones that Google, Microsoft, or Facebook maintain, large-scale ISPs, like Deutsche Telekom, AT&T, and large-scale internet exchange points. So these points in the internet that are interconnecting hundreds of networks at the same time. So to be a little bit more specific about what we'll do in this lecture, what you will learn essentially is how do we optimize the performance, the flexibility, and the reliability of these massive large-scale network infrastructures. So as you can see, I'm teaching this lecture entirely online. So this is, believe me, something I would wish I don't have to do. Unfortunately, we have to, at least for this semester. So we'll use Zoom as a platform, as you can also see right now, for the lectures, but also for the exercises. I'm teaching the lecture live, so I'm live right now. That means that we can interact with each other, and we'll use that over the course of the semester. That means you can ask questions to me during the lecture, and of course invite you to do so. So the idea here would be that you can ask questions using two modes. The first one would be to raise your hand, at least virtually, using Zoom. So in Zoom, if you actually look in the participant list, just at the bottom of it, there is a raised hand feature. So if you click on this button, your hand will appear in the participant list, and then we'll know that you actually have questions. When you have a question, we'll actually unmute you, and then you will be able to ask your question using your voice. You don't have to deactivate the video. Voice is enough for this lecture. If for whatever reasons for instance, you may have too much background noise, you prefer actually not to ask a question using your voice, you can also use the chat feature. And for this, you can actually send a message using the chat in Zoom to Romain, who is the head TA and also one of the co-hosts of this meeting. Romain will then relay your question back to me using his voice so that we keep being human at least. There will be other mediums that we'll use during the lectures, also regarding the exercises, and I will introduce them a little bit later. Let's come back though to the interesting things and speak a little bit about networking. So I told you that in this lecture, what we'll do is learn how to optimize the reliability, the flexibility, and the performance of networks. And I would like to justify or try to motivate you a little bit why this is an important topic, I think. And I want to take two perspectives. The first one is the perspective of you and me. We are users of the internet after all. We use the networks every day. And so why should we care about the performance of our networks? It's pretty easy, you will see. And the second perspective is the perspective of a network operator, like the ones who are operating these data center networks, ISP networks. And so what are their challenges in kind of like trying to optimize these three metrics? So the first thing is to think about you as a users. So I'm sure in this audience, there are a couple at least of people playing online games. So this is like a screenshot of Fortnite, which is one of the most popular games nowadays. So if you have ever played like a first-person shooter like Fortnite, you are like, I'm sure, deeply aware that network delay is key in these kind of games. And it can be extremely frustrating to actually play the game at all if you have like a too high delay towards the server. Actually, if you just type into Google Fortnite network lag, you will end up with almost 1 million reasons, 1 million web pages, effectively, explaining you how to actually optimize your network for decreasing the delay in Fortnite. So there are like countless and countless of pages explaining you this. And one interesting survey though showed that it's a survey from 2020 that almost half of the people experience actually bad network connectivity when they play online games. So that's for Fortnite, which is a live game. So you kind of like play the game live and you render the game locally on your machine. There is a new trend now in gaming, which is about streaming-based games. So the idea here is to actually render the game not on your device, not on your laptop, but actually on the server somewhere. And so the server can have like powerful graphical interface. And then the server will actually stream you the video feed of the rendered game. And so these games, that's kind of like the future, if you believe like the big players. So Google is in this business, Xbox, Steam, they are also there. And here, what is happening is that not only you need low delay, but you also need a high throughput, because now they are streaming at the same time high quality video feed. And I hope you can see on this slide, but in order to get like 4K resolution in Google Stadia, so this streaming-based platform, you need 35 megabits per second of connection, which is pretty significant. So here in streaming-based gaming, you need not only low delay, you also need high throughput. Of course, it's easy for me to mention this, and I'm sure you're like painfully aware of this now, but all audio video conferencing techniques and tools, they also need very good network quality. Otherwise, the user experience tends to degrade very quickly. And I hope this is not the case right now, that you are able to hear me and see the slides with a high quality. But surely if the network quality would go to degrade, this would not be the case very, very quickly. And needless to say, the same goes with video streaming. So I'm sure you're all aware of this circle of death that actually signify that there is a buffering events happening, for instance, during your favorite movie. So all these are problems I'm sure you and I have certainly experienced over the course of our lives now, connected over the internet. But where does this all come from? Why do we have so many problems possibly with our networks right now? And to understand this, we actually need to come back to the very root of networking and how the fathers and the mothers of the internet actually designed the internet in the first place. So if we look a little bit at this, and that's something we covered in detail in our introduction to communication networks, but in any introduction lecture, you will have seen this, I'm sure, that by default, the internet and IP networks in general, they only provide you with a best effort service. So what is a best effort service is simply, what does it mean? It simply means that IP routers are trying their best. They are trying their best to deliver the package to this destination, but they do not make any promises whatsoever. So you don't have any guarantees whatsoever of what can happen. So packets can be dropped, packets can be duplicated, packets can be delayed, packets can be corrupted. And essentially what we start to see is that let's say our usage of the internet continues to evolve, just doing the best, it's not enough, and at least for some application. So that's kind of like why we start to experience these problems as a user. So that was the first perspective, the perspective of you and I as a user of the internet. So what about the perspective now of an operator providing internet services? So an operator who tries actually to please you as a customer so that you keep paying the bill at the end of the month. So if you are an operator, it's also a tough challenge for you. So why is that? Well, first, as an operator, you are always more and more your network is always carrying more and more critical services. So what do I mean by this? So I mean services that can absolutely not fail. And one good example of this is telephony, for instance. So this is kind of like an excerpt of the Swisscom website. So Swisscom, since the end of 2017, so since a few years ago, all the fixed network services, including telephony, they run on top of IP technology. So essentially they run on top of their IP backbone. So that means that your emergency calls now, they go over the IP network. So whenever you start to carry services like emergency calls, you obviously care a lot about the reliability of your network. You also care a lot about the performance of your network. And you need to maintain this at all costs. It's absolutely vital, as you may, of course, imagine. So the same holds actually for other networks, like here at ETH. So at ETH, if you pick up any phone and you start a call with someone, it actually goes over the IP network. Even if you are using an analog phone, there's actually like, there is like an analog to digital conversion, which is happening using one of the hubs over there. But if you look over the ETH website, it's actually the network services now, which is responsible of telephony at ETH. So this is kind of happening everywhere, including at Swisscom and including at ETH. As I said, with great powers come great responsibilities. And the last thing you want is, for instance, your network to go down or your emergency services not to be reachable. And unfortunately, this happened recently for Swisscom, actually, in February 2020. So here, the emergency services were not reachable for more than an hour and a half, actually, because of a network issue. So that's terrible, of course. You can only imagine the bad consequences of not being able to reach these numbers when you really, really need it. So IP networks always carry more critical services. At the same time, IP networks, and I'm sure you will understand why as well, they always carry more traffic. And this is really like the confluence of three trends. The fact that us as users, we are always connected with more and more capacity at home over our phones. The fact that there are always more and more users, so the second point. And then the third point is that us, this kind of like users, growing user base with more and more capacity, we always consume more content. We want video, we want audio, we want like music. Everything now becomes connected. So when you combine all these three together, you kind of get an explosion in terms of like network traffic, still going on today. So let me just illustrate these points, which I think are pretty obvious. So first, let's speak a little bit about the speed of your connection, broadband connection, for instance, at your home, or cellular connection over 5G or Wi-Fi. So the expected growth in terms of average throughput by 2023, so in less than 3 years from now, it will be at least twice for each. So it's actually twice for the broadband and 3 times for cellular and Wi-Fi. So that means that the throughput we can get out of the network will kind of like more than double on average. Of course, these are numbers that have to be taken with a grain of salt from the point of view of Switzerland. So in Switzerland, we happen to be very well connected already. So for us, it's likely not to be the case that we will double, but on average, this number is true. And on the right-hand side, the right column, you can see actually the absolute number on average, which we are expected to reach by 2023. So 110 megabits per second on the broadband connection. So just to give you like a little bit of perspective, when I started to use the internet, I got like a 56 kilobits per second connection. So it's kind of like a world of difference between the two. As I said, in Switzerland, we are pretty well off. So if you, for instance, consider like the coverage already today in terms of like fiber connectivity, it's already one of the best. And Swisscom has actually communicated that by 2025, so in less than 5 years from now, the majority of the Swiss homes and business will actually have access to fiber connectivity. So with fiber connectivity, we are talking about connections at home that can reach a gigabit per second in upload, but also in download. Of course, that's assuming you're directly connected with a wire. If you're connected with the Wi-Fi, this is likely to be the bottleneck. So always faster speed, and this is not going away. At the same time, always more users. So again, in Switzerland, I think it's already 9 people out of 10 are already connected. So that will not grow that much, but at the scale of the entire planet, this is still growing. And so it is estimated that by 2023, there will be 5.3 billion people connected to the internet. So still growing strong and still going fast. This is still not the entire world population. So we still need to do better there, but it's still going on strongly. But it's not only that we have 5.3 billion humans using the internet. All of us now, we have multiple devices as well. So we have a tablet, we have a smartphone, we have a smartwatch, we have multiple, perhaps PCs, a laptop, a server. We have like IPTVs. So we have like so many devices now, each of us. And though it's actually now, it is estimated that by 2023, there will be close to 30 billion devices connected to the network. So again, as a network operator, you are pretty scared about this because each of these devices, obviously, they will consume throughput. So they will consume a little bit of your capacity. So you need to figure out how to design your network, how to maintain your network up to speed, and how to evolve it as well. And also, and this is also something that I think all of you will see because of the way our lives work now in 2020, but we always consume more and more internet-based content. So these are just like a few statistics regarding Netflix and YouTube that I could find. And these are statistics that are pre-COVID, so pre-pandemic. But what you can see, which is already huge anyway, is that, for instance, Netflix last year had close to 167 million members all over the world. So this for sure has grown a lot since then. And on the right-hand side, it's a little bit small, but you can see the number of YouTube users around these years as well. And you can see that by 2020, we are around 1.8 billion YouTube users. So all of them kind of watching videos, some of course in ultra HD quality. So it's a lot of throughput for each video. So we are talking about almost, for ultra HD feed, we're talking about almost 20 megabits per second. So as a network engineer, as a network operator, you of course look at these numbers and you need to dimension again your network for like being able to cope with this over time. So this is what I said. So all this ever increasing network traffic, that can stress your network infrastructure unless you have like over provision it massively. And so you need to actually take it into account. You need to track it and monitor it over time. And then you need to do something in order to avoid congestion. Otherwise, of course, your customer won't be happy for the first reason. They will start to complain because Fortnite doesn't work, before Netflix doesn't work in Swisscom, for instance, etc. So this is one example, again, like from 2020. So very recently, it was in March 2020. But you can see, and of course you can go on the and read the full article, but essentially it says that Netflix lowered the video quality to help ISP congestion, to help relieve ISP congestion. So this is somehow arguable though. So this is something that for those of you who have followed the communication networks lecture, you will know pretty well by now. But essentially so the way Netflix works is by trying to very aggressively peer with as many networks as possible in order to lower the transit bill. So for a lot of large ISPs in Europe, they are directly connected with Netflix. That means that if Netflix is indeed congesting the network, they are most likely congesting actually the peering link, because networks tend to be well dimensioned for that. That said, I'm fully with them that it could be indeed that for some of the ISPs, they indeed had an issue with like all these Netflix feed. And so for them, it actually made sense. But of course, they took like a measure at the scale of the entire Europe, which is somehow arguable. And some people actually complain about this as well. But all this to say that clearly like video traffic is putting a lot of stress on network infrastructure. And this is just one example of the consequence it might have. So that's what we'll see in this lecture, how you can optimize performance, flexibility, and reliability so that you as a user, you get the best experience possible, and so that you as a operator, you can actually provide this good experience. So that's kind of like what we'll see together. But the question, of course, that you will have now is, what do we do? I mean, what are the techniques that can actually help with solving these issues? And here, there will be quite a few that we'll see together. So here, we'll actually see together 6 different techniques, 4 of them related to performance. So how can we optimize the performance in a network? 1 related to flexibility, and another 1 related to reliability. So I want to quickly give you like a very high-level overview of each of the techniques, kind of like giving you a teaser of what we'll see together in this lecture, and also hopefully motivate you to continue and take the lecture fully. So let's look first at the performance aspect, and let's look at traffic engineering and load balancing taken together. And here I would like to consider a very simple example. So it's a small network. You can see that we have like 7 routers, R1 to R7, and we have 2 sources connected to R1 and R2 that are sending traffic to a destination which is connected to R5. And in this simple example, we just assume that each source is actually only sending 1 TCP flow to this destination. So there are 2 TCP flows in this network that are going from source 1 to source 2. And for the sake of the argument, we'll use the simple routing protocol, OSPF, with unary link weights. So all the link weights are 1, and as you know, OSPF implements shortest path routing. So the question to you is, what is the maximum throughput that the flow source 1 destination and source 2 destination can actually achieve in this network? So let's see if you can figure this out. And I've prepared a little poll. which hopefully will work. Oops. Okay. All right. So please answer now to the poll. Should be easy. So don't think too much. Just like what seems, let's say, intuitive to you. So we are reaching 40% of votes. So that still means 60% of you haven't clicked on the vote yet. So please do so quickly. All right. So let's end now, and hopefully I can share the reasons. Share the reasons. I cannot. Okay, sorry about this. This is all right. That's the first Zoom screw up of the semester. All right, though, let me give you the results, even though I think you can see them. But what I see on my screen is that 67% of you clicked on 5 gig per second, which actually is indeed the answer I was looking for. So the maximum throughput, assuming, of course, that the flows are all active at the same time, the two flows will compete with each other. And as you can see, I hope on the network, because of shortest path routing, they will share the upper pass of the network. And they will collide, and then TCP congestion control will do its job. And then they will reach in the steady state 5 gig per second. So that's kind of annoying, because in this network, assuming all the links are 10 gig per second, what we see is that we are kind of like not using the entire lower pass. So there is no. All right, that's it for polls, I think. Essentially there is unused and wasted bandwidth in our network. So what can we do better here? So again, like, what is the problem? Well, the issue is that shortest path routing essentially computes one single pass between R3 and R5 and only uses this one. So all the traffic is essentially flowing along one pass, while there are actually two available in the network. There is the lower pass that we do not use now. So because we are using shortest path routing, what we are doing in order to influence, or what we can do in order to influence shortest path routing, is essentially modifying the weights. So here, what we can do is, for instance, increase the weight of the upper path. Instead of 2, for instance, making it 3. And if we do that, then we'll be able to profit from what is known as equal cost multipass. So for those of you who have followed our lecture, you know that equal cost multipass, or ECMP, this is a routing strategy in which IP routers can split traffic over multiple best paths. In the case of OSPF, best means shortest. So if there is one more or more than one pass with a minimum cost, then you can actually split the traffic on all of them. So here, the easy solution, for instance, is to pick one of the two link, R3 or 4, or R4 or 5, and then increase the weight to 2. And then you get the upper pass with a cost of 3, and then the lower pass with a cost of 3 as well. So assuming R3 is indeed implementing ECMP, R3 will start now to have like 2 pass to reach the destination. So that means that it will have 2 minimum cost pass via R4 and via R6 as next step. And then load balancing can start to happen. So you can see that by modifying here a single weight, I could actually start to increase the pass diversity at R3. But of course, this is kind of like a super simple example, right? You have like one destination and here 2 sources. So the problem becomes very complex as you have like many destinations that can be everywhere and many sources that can also be everywhere. Actually, the problem becomes NP hard if you have seen like theory of computation, if you know a little bit about complexity theory. So that's kind of like a hard problem, and that's one of the problems we'll actually see in practice how we can solve that. But that is not enough to fully start to utilize the network. So one of the issues we have is that even though R3 here has 2 paths to reach the destination, via R4 and via R6, R3 needs to split the traffic over these 2 paths. And for that, R3 needs some logic as well in order to load balance the traffic over these 2 paths. And so the limitation comes from the fact that right now in existing devices, in existing routers, most of these devices, they split the traffic using stateless hash function. So essentially what is going on, you have like the router, R3, receive IP packets that are going to R5. And what the router will do is essentially compute a hash function on the IP header of all the packets going to R5. And then the hash function will be made modulo the number of next stop, like 0 or 1 in this case. And that is how the network will actually, or the router will actually split the traffic over the 2 paths. So the cool thing with this technique is that it's completely stateless. So the packet arrives, you compute a hash function, you get either 0, you send it to R4, you get 1, you send it to R6, and you don't need to maintain any state. And the cool thing as well is that if you compute the hash function on the 5 tuple, so source IP, dest IP, source port, destination port, and protocol, TCP, UDP, then you are guaranteed that all the packets of the same TCP flow will follow the same path as well. That is kind of nice because you may remember, but TCP doesn't like reordering. So that actually hurts the performance of TCP quite badly. What can go wrong though? Perhaps you have seen it already, but what can go wrong is that this hash function might actually return the same value for the 2 flows. So again, remember we have 2 flows from source 1 to destination and source 2 to destination. So it could be that we are unlucky and that the hash function returns, in this case, for instance, both 0, meaning that all the traffic goes to R4, or both 1, and then all the traffic will go to R6. So ideally, we would like to be lucky all the time, and that the hash of each flow, in this case, would always return different values. So either 0 or 1 or vice versa. In this case, then we could actually fully utilize the bandwidth of the network. But again, it's a stateless function for good reasons, because it's hard to maintain state in routers. So that's not what we get. So it could be that it doesn't work well in practice because of these collisions. Actually, it will work well when you have like many flows that are all the same size. In this case, they will actually start to, on average, spread very nicely over the 2 paths. But if you have like very few flows, then they can actually clash with each other, especially if they are pretty big, like in our example, of course. So in this lecture, we'll also see how we can improve that. So essentially, how not only can we compute more paths in our network so that we can start to utilize them, but also how can we actually load balance the traffic over all these paths. So we'll use 2 techniques, or we see 2 techniques together in order to learn about this. The first one is smarter load balancing function. So we'll actually go beyond just stateless hash function, and we see how IP router can actually load balance traffic using, for instance, queue occupancies. So they can monitor in real time what is the state of their queues, of their buffer, and then immediately see that there is congestion on one queue, for instance, that's moving the traffic accordingly. We'll see our routers can even start communicating with each other in order to actually know what is the downstream pass load. So it could be that you are not loaded, you are not congested, that let's say you as a router, but it could be that someone downstream of you is actually congested. We see how we can leverage packet interarrival time or random functions as well to improve this. So we see quite a few load balancing functions that enable us to do that. That will be the first kind of techniques we'll see. The second set of techniques we'll see is related to label switching. And label switching will be used a lot in this lecture. So it is actually a very important tool to know about. So we'll deep dive into that. And it's, I must say, used in a lot of big networks again, at least all the ones I know of. So the idea of label switching is to go beyond just IP-based forwarding. So one of the issue here when you are R3 is that the 2 flows are going to the same IP destination. So since you are doing like IP-based forwarding, then you will always send them on the same set of path because you cannot distinguish them. They are all going to the same destination. So the idea of label switching is to kind of like break these dependencies on the destination IP to forward as a forwarding decision, and to actually introduce a label and to kind of like forward traffic according to that label. And so here you can see this on the slide. You have like a plain label and you have like a line stripe label. So what you can have is you can ask R1 and R2, which are the routers on the ingress of the network. These are the routers that are receiving traffic from the host. You can actually ask them to slap a label on the packets and then to send a label packet down to R3. And now you can see the traffic that comes from source 1 and the traffic that comes from source 2, they will have different labels, which of course enable now R3 to start distinguishing them because they're not going to the same IP destination anymore. They also have another label now. So that's an interesting thing for R3 because now they can start using the path. And we have our first question. So let me unmute you. Yeah.
I'm sorry, you considered, no, Romain asked me to raise my hand for testing.
Okay, perfect. That's fine. Okay, so it works, I can tell you. All right, so another. Okay. So label switching. Essentially, how can we slap labels on a packet and so that we break the dependency to the IP address. So this will be the first part of performance. So as I said, we'll see traffic engineering. So how can we compute more paths in a network and better paths in a network, and then load balancing over all these paths. So we see techniques to do both actually together. So this will be the first block in the lecture related to performance. So after, we'll start to see quality of service. So here, the intuition with quality of service is that whatever you do, even with the best traffic engineering in the world, even with the best load balancing in the world, you cannot always avoid congestion. Congestion is kind of like a fact. It will happen eventually. You can try to lower the occurrences of congestion, but sooner or later, you will run into a congestion event. And when that happens, you can either do nothing and just let the network, like the routers in this case, start dropping packets, or you can also take control of it. And that's the idea behind quality of service. So you can think of quality of service as a set of tools that enable you to manage congestion, essentially, which is actually, I think, interesting for you, the audience, because for instance, a lot of time, if you think about you as a user again, a lot of time the bottleneck will be very close to you, sometimes even in your home network, like your Wi-Fi gateway, not to name it. So a lot of Wi-Fi gateways or routers that you are using, they actually offer you the possibility to configure, the capability to configure QoS, quality of service. So by kind of like learning about these techniques, you will be able, for instance, to improve your home network thanks to them. But of course, operators are also using these techniques internally inside the network to kind of like make sure, for instance, that emergency calls, like calls in general, take over, let's say, video traffic. So you can start to do things like giving priority to one type of traffic over another so that you will always drop video before you start to drop, let's say, calls to one of the emergency numbers, which of course makes a lot of sense. Of course, that's one way to handle congestion. You could also kind of prevent, even using traffic engineering techniques, you could even prevent the flows from ever going over the same link. But that, of course, is a decision that makes us a lot of money because you might not be able to always avoid, meaning that then you might need to add extra links to your network in order to enable that. So we'll actually see a lot of QoS techniques together that are kind of summarized in this picture. So this describes actually in like a succinct manner, the pipeline of a QoS-enabled router. So you have like input links on the left-hand side, and you have one output link on the right-hand side. And essentially, QoS are these kind of like let's say 5 or 6 basic building blocks that are in between. So with QoS, we'll see how we can classify traffic, for instance, into high priority, low priority, or like gold, silver, and bronze type of traffic if you want. So we'll see how we can classify traffic. Shaping and policing relate to how we can essentially enforce a throughput for some traffic. So for instance, how can I force you to not over-consume the network throughput? So for instance, with shaping, I can throttle your connection to 10 megabit per second. And policing is the same kind of like techniques, but instead of like throttling, slowing you down, I will just drop the packets if you ever go above 10 megabit per second. So shaping and policing will be techniques to kind of like regulate the throughput in the network. We see multiple buffer acceptance algorithms. So these are like logics or algorithms, procedures, if you prefer, that are used in networks in order to figure out whether a packet needs to be dropped or not. And then we'll see multiple queuing and scheduling strategies. So in QoS-enabled routers, you have multiple queues, and these queues can be served according to different schedulers. So for instance, you can have one queue which is always high priority and will always be served whenever there is a packet there. You can use round-robin strategies, weighted round-robin strategies, et cetera, et cetera. So there are like quite a few strategies that are used in practice, and we'll see them together as well. And so using these different building blocks, what you can essentially do is take control of congestion. So when congestion happens, and you know it will happen at some point, at least you can say, don't drop my emergency calls, only drop video. If you don't do that and you don't enable QoS, anything can happen. Your VoIP call can be dropped, your emergency calls can be dropped, your video can be dropped as well. All right, so this is QoS. So traffic engineering, load balancing, QoS. So these are three heavily used techniques to improve the performance in the network. Something else we look at is multicast. So multicast is a technique which is heavily used to actually carry video in like ISP networks. So here I want to take a very recent example. So I'm sure that some of you, at least again in the room, if you're not gamers, you probably have watched the Champions League final that happens between the Bayern and Paris Saint-Germain a few weeks ago. And so I think for a lot of you, you actually watched the game using, let's say, your set-top box at home. So that means actually the video feed was coming to you using the network. So how do you actually either start to think about delivering live video? So we're not talking about Netflix movies, right, that are like on demand. We're talking about live video, and you want really everyone to see the same video more or less at the same time. So it would be terrible, for instance, if you imagine a street in Zurich, and like because of network delays, you would have some houses that see the goal way before others and start screaming before the others. So you don't want this. You want essentially all the households, possibly in Switzerland, to be able to see the Champions League final at the same time without basically blowing up the network. So these are actually statistics that come from this year's final and about the number of viewers in France and in Germany. And here, so we're talking about more than 10 million in both. So 11 million and almost 14 million in Germany. So 25 million people. And each looking possibly over their IPTV box. And so most likely using HD or Ultra HD quality. So 8 megabits per second, so 25 megabits per second. That gives you essentially throughput that are reaching hundreds of terabits per second. So there is no way this is how it works, right? And indeed, this is not how it works. So if we look, for instance, now, let's go back to Switzerland, and let's assume, for instance, that the server, which is supposed to actually stream the video, is located here in Zurich. So the server is receiving direct the live feed. In this case, I think it was from Lisbon that the final was taking place. So let's say the live feed comes from Lisbon directly to Zurich, and then the Zurich server is responsible for spreading this video across the entire country. So how do you do this? So again, you cannot just assume, let's say we have 1 million people watching the game in Switzerland. You cannot just have 1 million connection that are like just like one streaming one over the other. So they don't do that. What they do is that they actually leverage network devices to multiply the traffic automagically. And so this is this technique which is called IP multicast. And with IP multicast, what you can do is essentially ask the device so the routers, to not only send a packet once, but actually to multiply a packet when you send it. So a router will receive one packet, let's say one frame, and will actually duplicate it into, let's say, 100 frames. And you can do that at every single hop. So essentially what you can get there is kind of like an exponential increase, if you think about it, of the traffic. And this technique is actually the one which is used in powering all the kind of IPTV that we have today. So it's kind of like heavily used tonight, for instance, at home. Again, if you are using one of the, let's say an IP-based television, and you are turning it on, you will use IP multicast to watch it. All right. So these are the techniques we'll see together for performance. So we'll see traffic engineering, load balancing, QoS, and IP multicast. So the next topic will be about flexibility. And here we'll see together how we can virtualize a network infrastructure. So let me explain a little bit what I mean by virtualizing a network infrastructure. And let me speak about virtual private networks. So here, let me perhaps give you an intuition. So the idea is that oftentimes, as a network provider, you have built a pretty extensive network infrastructure. So if you are Swisscom, you just imagine the physical network that you have built covering the entire Switzerland. So it's very tempting for you to provide a service to other companies, for instance, banks, like here Credit Suisse and UBS, that would enable them to actually communicate between all the branches across Switzerland. So by doing this, essentially what you would like to do is kind of like virtualize your network so that it appears to Credit Suisse as being the Credit Suisse network, and it appears to UBS as being the UBS network. So this is what I mean by virtualization in this case. So here, let's consider this simple scenario. We only have 4 sites, 2 of each banks. So in Paradeplatz, Bellevue, Bahnhofstrasse, and Central. And so what we want is that the 2 branches of Credit Suisse should be able to exchange traffic with each other. And of course, the 2 branches of UBS should be able to exchange traffic with each other as well. Of course, what we don't want is that the branch, even though they are discussing about merging, if you have followed the news, we don't want, for now, we don't want the branch from UBS to be able to exchange traffic, at least directly, through us with the branch of Credit Suisse. So essentially, as Swisscom, you need to kind of like provide these services where branches can discuss with each other, but only with kind of like if they belong to the same customer, in this case, Credit Suisse or UBS. So there is a twist here though, because you might think, well, this is actually pretty easy. I'll just give different IP subnets to each of them and then I'm done, right? So why is there even like something to be done special here? Well, the problem is that if you remember your introduction lecture, there is this concept of private IP space that many companies, of course, use internally. And so it could well be that, for instance, Credit Suisse internally use 10/8 type of IP address, and that UBS internally also use 10/8 type of IP address. That is totally okay, and it's actually likely that they are doing this. So that means that as Swisscom, right, you cannot really base yourself on the IP address anymore in order to forward the traffic, because it could be, for instance, that the same IP belongs to Credit Suisse and UBS because it just happens to be in the same private IP space. So this is kind of like the problem we had before, right? If you see a connection with traffic engineering context, is that in our network today, we often have a dependency on this IP address. And so if you imagine, let's say the Bahnhofstrasse branch sending an IP packet to 10.1.0.1, then the Swisscom network wouldn't know whether it should deliver it to Credit Suisse or UBS only based on the IP address. And so here we'll again use a technique to break this dependency apart, and we'll actually use label switching again. And the idea is quite simple, and I will finish with that before we do the break. Is to just give each site, so each customer, like Credit Suisse, UBS, a different label that identifies them. So you could have, again, like the plain label or the striped label. And then we'll actually configure, or like have a protocol, it's a little bit more precise, running at the ingress of Swisscom that will actually set or slap these labels on all the packets that we send, for instance, from a UBS site or from a Credit Suisse site. So that means that all the IP packets now, they will not only carry the IP destination, they will also carry a label. And that will enable actually the routers within Swisscom to disambiguate now and not actually start sending traffic from UBS to Credit Suisse and vice versa. So here it will be pretty clear that since it's a striped packet, that it will actually go to UBS. So that looks pretty simple. And the principles are actually not that hard. But you will see that you need quite a lot or an involved, let's say, machinery in order to make this happen. Because of course you want these labels to be computed automatically, to if there is a failure, so that they are recomputed if needed. So it's something that you need to actually take care of. And actually we see that BGP, the interdomain routing protocol for some reasons, is actually used in order to move these labels across the network. So that's surprising, but this is actually one of the big use of BGP today. That may look like kind of like a basic service, but actually this kind of like virtual private network service, it's really bringing a lot of revenue to the big ISPs. It's actually something that they care a lot about because, of course, as you may imagine, it's not only about the banks. Many companies, of course, want to interconnect the different branches together. All right, so that's a lot of techniques already. So what I propose to do is that we do a short break now until, let's say, 3:15. And then I will continue with the rest of the technique. I'm almost done anyway. And then I will talk about the, what is it that we're actually going to do and how we'll organize the lecture. And then we'll dive into network programmability, which is kind of like the cool and upcoming topic as well in networking. And you will learn all about it during the lecture. So let's make a quick break now and let's resume at 3:15. Welcome back. So we have seen together already a couple of techniques, and we'll see one more. And so one thing I would like to mention that I received some feedback during the break already. So as you can see, I'm not using, let's say, a default zoom setting. So there is this switching between the video and the slides. I hope it works well. It looks like there might be some delay between the video and the sound, which I understand would be very annoying. So if that's the case, perhaps you should actually let us know so that we can try to make sure that next time this doesn't happen anymore. Anyway, so let's go back to the lecture now, 45 minutes of lecture, and then there will be again another break, and then the first practical exercise session. So as a reminder, we have seen how we will kind of like learn how to improve performance and how to improve flexibility. So now let's see how we can improve reliability also in our network. And for this, I would like to speak about fast convergence. So fast convergence is the problem of how do we make IP networks converge faster than they converge by default when there is a failure. So if you think about a massive network that composed of like, I don't know, thousands and thousands of devices like in a data center or like in a huge ISPs like Deutsche Telekom, they see failures every single day, multiple of them. And so for every single failures, traffic might be disrupted a lot. And again, as I've mentioned initially, right, as a user, you don't want your traffic to be disrupted. It could be actually very important, let's say, VoIP call that is going over these links. So it's very important that we find techniques that enable the network to react fast to these failures. So as I said, though, by default, it's not the case. So by default, networks converge pretty slowly. And so we actually did the measurements here. For those of you who have followed ComNet, perhaps you have seen this already, but we took one of the ETH router. So at ETH, we are lucky to have like actually pretty recent routers in our network. So these are Nexus 7 9K. So these are, Nexus 9K. So these are actually pretty good routers. And we have, I think, dozens or 20 or so in our network. And so we were lucky enough to actually be able to test on one of them, what is the time this router actually takes to converge when there is a failure. And we measured that in the lab. So we went there, and then we actually plot this on the graph. And so I will show you this. So on the y-axis, you see the convergence time, which is expressed in seconds from 0.1 to 150 seconds, so multiple minutes. And on the x-axis, you can see the number of prefixes that the forwarding table of that router was actually carrying, ranging from 1K to 500,000 entries. And these are the convergence time we measured. So worst case and median case. So as you can see, traffic actually was lost for almost 2.5 minutes. Not all the traffic, but the traffic for some of the prefixes was lost for almost 3 minutes, 2.5 minutes in this case. That is huge. So this is something, of course, if you are the user again, if you are, let's say, in your Fortnite mode, right, and you are in the last man standing, and then the network goes dark for like 2 minutes, of course, you won't be very happy. Same thing if you want to place a call, if you want to have like a video chat with anyone, this will not be nice on you. So of course, this is way too long. And so, but this by default is the kind of convergence time we see and observe routinely, actually, in networks. So why does it take so long? Well, if you think about convergence, we have to decompose the convergence event into its different pieces. So of course, if you think about a failure, the first thing you need to do before you can converge is to detect that there is a failure in the first place. That takes a little bit of time. You need to detect the failure, then a router needs to report that there is a failure so that the other routers around it can start diverting the traffic. So you report the failure, you generate new routing messages, for instance, telling the others that that link is not available anymore. You need to recompute the path accordingly. You need to communicate this new path to the hardware. So you need to tell now, perhaps, I don't know, in our example, up to 500,000 entries that they need to go not only to router 3, but now they need to switch to router 6 as next steps, for instance. And then you need finally the hardware to install these next steps. So on the right-hand side of the slide, you can see the average time that each of these operations take, like an order of magnitude roughly. But you can see what is clear there is that there is one big bottleneck, is actually the communication of the next steps to the line cards. So that takes a lot of time. So these are numbers per entry. And you can multiply this by a lot of entries and end up with actually minutes, as I was mentioning initially. So in the lecture, we'll actually see how we can make things better. And there's been a lot of research and a lot of developments in what is known as fast reroute technology. So fast reroute technology is essentially an ensemble of techniques that can be used by routers in order to converge super fast. So we are talking sub-second convergence or even sub-50 milliseconds convergence in some cases for independently of the number of prefixes. So to retrieve connectivity for all the destinations. So that's kind of like the goal. And that's the golden rule, if you want, if you are like a network operator and you are carrying like critical traffic, again, like emergency calls. So you want a network that can converge all the time within 1 second. You must actually have this. So here we'll see, for instance, how we can leverage the hardware to accelerate the detection of failures. We can see how we can pre-compute things. Clearly, we don't have the time to compute just when we learn that there is a failure. We need to pre-compute. We need to be ready so that when there is a failure, we can immediately activate the new paths that were computed before. Of course, computing any possible things that can happen and maintain state is costly. And so that's something that we need to actually handle, and we see how we can do that. And then there is a problem that, as I've told you, the main bottleneck is to actually communicate. It's the communication channel between the software and the hardware. So we have detected, we have pre-computed, but we still need to let the hardware know that now it needs to forward traffic differently from before. So here as well, we see that pre-computation usually goes hand in hand with pre-provisioning, and we see different techniques to activate the backup state that we have pre-provisioned. So we see all these kind of techniques that are used, again, like in production environment all the time. That's kind of like the, let's say, the state of the art, if you want, in fast reroute technologies. So that's kind of like the plan of the lecture. You can see quite, I hope, interesting for you techniques to improve the performance, the flexibility, and the reliability of large-scale network infrastructure. So that's great. Oops, sorry about this. All right, okay. So that's great. We have learned that hopefully you care about performance, you care about flexibility, you care about reliability. And also we have now techniques that I will teach you in order to implement these kind of like solutions. But how do you actually do that in practice? And so that's something that if you have taken ever a lecture with me, you know that in our lectures, we tend to be quite practical as well. So it's not only about teaching and learning about principles, you also have to play with them. You even have to implement some of them. And this lecture is not different at all. So in this lecture, not only will you learn about the techniques per se, you will also learn how to operate them, and you will learn how to implement them. And so again, for those of you in the audience who have followed our communication networks course, the basic introduction course previously, you know already about operating your own network in a virtual environment. That was the mini internet project. For those of you who have not taken the lecture before, it's okay. You will just learn about it in this lecture. But essentially, we'll give you in the lecture, we'll give you the ability to play with your own little network. So each of you in the room will have your own network, and then you will be able to operate the network as a network operator. So you will be really able to play with the technologies and see how you can actually manage them in practice. So that will be one thing that you will do during the exercises and also during the project. Of course, I will mention the project in a minute. So that's one thing. How do you operate your network? And then another thing, which is, I think, quite exciting as well, is that you can actually now, in modern network technologies, you can even re-implement your own logic. So you can not only configure existing protocols, you can create new ones from scratch. And so that's something we'll see a lot in this lecture, is the concept of network programmability. So we'll see this language, which is called P4. That's a programming language that will allow you to implement your own forwarding logic. So you will be really able to implement your own network device if you want, and actually tell them what exactly they need to do. So here I want to mention a little bit more about network programmability. So network programmability is a very exciting trend in our field of research. It has been going on for around 10 years, and I can ensure you that a lot of people care, both in the industry and in academia. So I just want to actually illustrate this with some concrete numbers. So let me first explain what network programmability is and what it means by this. So until recently, networks were kind of closed down completely. So you had like Cisco devices, for instance, Juniper device, Brocade, Force10. It's like many vendors providing you with routers, switches, firewalls, etc. And these devices, they had closed software and closed hardware. So the only thing you could do is really wire them up together and start configuring them. But you could not really change their behavior beyond the configuration. So why is it exciting now in networking? Is because now the devices are kind of like completely open. So what we have and what we have more and more in modern network is open source software. So like think of like Linux for your network. So open source software, meaning you can of course modify it, running on top of standardized interfaces that are used in order to communicate with reprogrammable hardware. So hardware that you can control and modify the behavior of. So almost everything in this picture now is programmable. You can kind of like change the behavior as you wish. You can change the controller. You can change, for instance, the kind of logic you use in order to compute paths, so to do traffic engineering, load balancing. You can use this open interface to then communicate with a reprogrammable hardware that you can also, that is malleable, that you can also change the behavior of. So P4, again, is a language to kind of like program this reprogrammable hardware. And then OpenFlow is one example of an interface that can kind of bridge the controller and the hardware together. So it's the interface between software and hardware. So everything is open now, pretty exciting, actually, things. So as I said, this is attracting a lot of industry interest. This has been going on for like almost a decade now. So you can see here on the slide, on the left-hand side, this was the first acquisition, really big acquisition in the world of programmable networks. That was Nicira, which was kind of like a Stanford startup that was acquired for 1.26 billion by VMware. That was actually the biggest, I think, acquisition, certainly in the world of networking of the year. It was in 2012. And essentially, Nicira was kind of like pushing for this standardized interface, this OpenFlow. And they were pushing that in the context of the data center network. And so that was very interesting for VMware, which is also active in that domain. So that was in 2012. And then other people at Stanford created another startup immediately after that was looking at reprogrammable hardware. So not only like opening up the interface between software and hardware, but also opening up the hardware itself. And so the startup is Barefoot Networks. And essentially they created these kind of like switches with reprogrammable ASICs, so with like, for which the logic can be programmed using a programming language, in this case, P4. That startup was acquired by Intel in 2019, so just last year. So like a lot of movements in the community around that. The amount this time was undisclosed. I don't know how much they have paid for it. Probably a lot. So as I said, this programmable hardware, you kind of like, of course, can reprogram them. And to reprogram them, you need a language. And P4 is the domain-specific language that describes how a switch should actually process packets. So you will play a lot with P4 in the lecture because it really enables you to actually implement the techniques that we see together as well. So not only will you learn about them, you will also see how you can implement them and then even have them running in the network. So that's actually an excerpt of our lab here in the group. So the cool thing with this hardware is that you can really buy it. I mean, it's not just like a research paper. These is actually devices that you can buy. And that's a sneak peek at our lab. You can see that we have, like in this case here, 8 reprogrammable switches that come from Barefoot Networks, each of them with 32 ports, with each of them has a capacity of 3.2 terabit per second, which gives us in this rack a total capacity of 25.6 terabits per second. So just to put this a little bit in perspective, but 25.6 terabits per second it's actually huge throughput. That's actually 3 times more than what the largest IXPs in the world are currently seeing after COVID. So if you go on the DKIX website, so if you remember, DKIX and AM6 are 2 very large IXPs, and the current peak rate of DKIX, at least when I took the screenshot, was 8.6 terabits per second. So it's 3 times. Well, we can actually handle, using these 8 switches, 3 times what DKIX is currently saying. So it's not only that these devices are reprogrammable, but they're also very fast, actually, which is nice. So it's not because usually when you have more flexibility, you lose a little bit in speed, but at least here, this is not the case. And we'll see why. I mean, it looks impossible, right? We'll see actually what makes this possible in the lecture, of course. All right, so that was for the practical part. So as I said, it will not only be a lecture about theory and like where you will be bombarded with like new protocols and techniques. It will also be a lecture where you'll be able to play with network technologies and new network technologies. This P4 language is really state of the art, at least in the community right now. So it's really something relevant that a lot of people care about, also in the industry. So that's something you can also use in the industry for your next job, but also as a researcher. And this I will speak next week. P4 enables us to do many more things that we could do before. So a lot of our recent papers, if you look on our webpage, actually use P4 as an implementation, let's say, manner. So we kind of like implement the techniques using P4, and we can show in the lab that they work at terabits per second. So it's very interesting for us, and I hope for you as well. So that's for what I hope motivate the kind of like problem we'll see, the kind of techniques we'll see, and also to tell you that this is not only theory, this is also practice. So now let's speak a little bit more concretely about the course organization. So as you probably have seen in the course catalog, the course will be divided in 2 blocks. So there will be first 10 lectures like now, every Tuesday, and 10 exercise sessions. So this will last around 10 weeks. And then there will be a group projects where you will use the techniques and your P4 and network programmability experience in order to perform a challenge. This will be done in teams of 3 students. And the project will last for around 4 weeks. So the lectures, as I said, nothing too fancy here. We'll have the lecture between 2 and 4, the exercises between 4 and 6. Of course, both will take place online as now. So hopefully Zoom is going to work pretty well. Again, if you have feedback about it, please let us know. And the group projects, so that's something we're still putting up together. But the idea is that you will actually participate in a class-wide challenge. So we'll take actually all the students in the class, and then we'll actually make you compete with each other. And the challenge is pretty simple. So you will all get your own network. It will be the same network for everyone. And then that network will need to perform tasks like sending traffic between source and destinations. And we want to make your network the fastest one. So there will be a leaderboard, and then you will really be able to use all the tricks in the book, including, of course, all the P4 fanciness you want, and all the fancy, traffic engineering, load balancing techniques you may think about in order to make your network beat all the others. So this, I hope, will also render the project exciting so that you can kind of like show us how creative you are, let's say, in actually finding solutions we probably have not been thinking about. So that would be also something we learn, we learn something as well as you are like making the challenge. So as I said, it's still under preparation right now. So we'll provide you with more information about the project in the coming weeks. So stay tuned for this. I can already tell you though that there will be prizes for the best teams. So that's also to give you another like motivation perhaps to be the best team of the class. Your final grade, probably you care about this as well. So it's not only about the prize for the project, it's also about your grade, right? So simple key of repartition, 70% for the exam. It's a written exam. So if you have heard about the lecture last year, it was an oral exam, but we have too many students now, so we have to switch to a written exam. And the group project will count for 30% of your grade. And so here we'll essentially grade you based on your code, the report, and then a presentation that you will have to do at the end. We'll probably organize a kind of like virtual poster session so that it's a little bit more interactive as well. So again, there will be more details coming up, of course, in the rest of the, of the lecture. So the exam, I'm sure you have questions about this as well. Well, it's the first time we make a written exam in the lecture, so it's a first for us. Well, of course, we know that of course, you want to know what is coming up at the exam, so we'll make our best during the lecture to actually give you examples of what we expect you to be able to solve at the exam. So it's a master level lecture, so it will be higher level questions than the bachelor level lecture. So just to give you a few examples here, but we could, for example, ask you to solve a high level problem, like a situation that would require you to, for instance, use all or subset of the techniques we have seen in class. And you could, for instance, like explain pros and cons of your solutions and why you actually go for that. So a kind of like design question. We could give you a design which is already pre-made and ask you to optimize it. We could give you like a P4 program and ask you to look at it and tell us what it does, whether you see that something can be improved or is it correct at all. We won't ask you to code at the exam, so there won't be a question where you need to start writing down code. But again, like since you have done the exercises, you should be able to reason about the program. So that's something that you should be able to do. I want to stress here, though, that because of this, of the fact that we can also ask you questions that pertain to network programmability, it's really important that you do the exercises. So you will be well trained, I can guarantee you this, during the semester about using all these languages and this reasoning about networks, but only if you do the exercises. So it's really important for you to do that, and the projects. Yeah. All right, so that's for the grade. For the team, so we have like, I think, a huge team of teaching assistants. So if you look at the normal lecture at ETH, I think we are way past the normal ratio of assistant to a student. So that means that I think you should expect great support, and I hope we will deliver again this. So we have like not less than 10 members of our groups that will help you over the semester. So Romain, as I said, co-host today, but he's also the head TA. So if you have questions pertaining to organizations, especially, you can directly contact Romain. And then some of you might already know some of the members already from previous lectures, but you will see these faces and you will interact with all of them during the exercises, of course, already today, but also during the project. And I also want to give a shout out to Eric and Yannick, who are students from last year, will also help you this year. So they're also, the rest being PhD students. So yeah, that's for the team. As I said, you will interact with all of them very quickly. We will use Moodle as a platform. So of course you should check it out very regularly. So the link is available on. I mean, you should find the link directly on the course catalog. There is a link there. You can also just look for the name of the lecture on Google. You will also find the website, the former website of the lecture with a link to Moodle. I'm sure you will find it. And of course, what we'll post on Moodle is all the material of the lecture. So, and I think that was one of the questions. The slides, for instance, will be put in advance. It's just this week. I didn't upload the slides in advance, but starting from next week, the slides will be available before the lecture so that you can take notes as well. So slides, extra references, links to exercises, etc. They will all be placed on Moodle. Also, something which is important to mention about Moodle is that there are like forums that you can use to ask questions. So we will be reactive and we'll answer to them. You can also, of course, answer to questions of your fellow classmates, so that if you have an answer, you can help us as well. And there is also like an introduce yourself forum, which I would actually encourage you, all of you here, to take, let's say, 2-3 minutes of your time and write a quick post in that forum that tells us a little bit what you are expecting for the lecture, why did you take the lecture, what interests you, so that we can perhaps actually try to incorporate some of it as well during the lecture. So it's still malleable as well. So if you have like 5 minutes later, please take these 5 minutes just to write a quick post and introduce yourself. Also, of course, it's online, right? So we lose a little bit of the human contact because of that. We are well aware of this. So we would like also to create some kind of like, let's say, more connections also within the students. So I think it's important that you try to interact as much as possible. And that's also why I think the class-wide project and challenge will be nice to kind of like also get you to know your fellow classmates. Another actually way to communicate with us, but also your colleagues and also your classmates is to use Slack. So I'm sure a lot of you by now know what Slack is. It's a chat client. And we'll use it to actually discuss about the course, the exercises, and the projects. So we have created a workspace already. It's again available on Moodle. So I would ask you to actually register today to the Slack workspace. So the URL is there. Please use your real name so that we know who you are. We will never post anything private on Slack. So it's really just like as a way to facilitate communication, quick communication between you and the teaching assistants, for instance, or between you and your team. So see that as a place to kind of like have quick discussions. As I said, like if you have like more like questions that require a little bit more thinking and that are longer to answer, it's actually better to ask them in Moodle so that we can also keep track of them a little bit better. So a chat client is not the best to keep track of a lot of questions over time because they would just be drowned in the history. So a forum is much more adapted for that. So please do register on the Slack web workspace and start asking questions over there, for instance. All right, so an important question now, which maybe some of you have, is that, or you have not made up your mind yet, is that should you actually take the lecture at all? And here my honest answer is that if you like communication networks in general, if you like internet technologies, you like to think about data centers, ISPs, all this kind of stuff, I think you should definitely take the lecture. There is a but, and I want to be fair, and I want to mention this in advance. If you really don't like programming at all, then you may not like, of course, you may not like the practical aspect of the lecture. So if you really hate programming, then I think the lecture might not be appropriate for you. It's not like an algorithmic lecture at all, but we will use P4, we'll use domain-specific programming to actually do networking-related tasks. So if you really don't like programming at all, perhaps then in this case you should reconsider. If for whatever reasons, and of course I'm very well aware it's a special semester for you and for us, but if you, for whatever reasons, you think that you may not be able to work that much during the semester, then you should also perhaps reconsider or consider discussing with us a little bit about this. Because as I said, there will be these exercises that you will have to do that kind of like prepare you for the project at the end so that you can actually use P4 for like make your network fast. So it's important that you are able during the semesters to actually learn about this technology. So if you really cannot during the semester, again, please contact us in advance because that may be a problem and I don't want you to run into issues towards the end of the lecture. Also, and I know perhaps some of you expect this, we don't have 10 years of exam history. I mean, the lecture is still very young, so we have been giving it 3 times, but this time we kind of like changed the content quite a bit and we will give a written exam for the first time. So we cannot provide you with a long list of let's say, exams from the previous year. But what we'll do, as I said, is really we'll try to actually provide you with as much hints towards the exam as we can during the semester. So that was also the problem for another lecture we gave ComNet actually, and at the very beginning. And I think the students actually were happy with the kind of like guidance we gave through the semester. So if you are not in this category though, and as I said, if you like computer networks, I really think you should take the lecture. I think you will, I really hope you will love it. As I just said though, we have kind of like revamped the lecture quite a bit. So every year we try to make the lecture better. So we work very hard on these lectures. And so a lot of the content will be new. Also the fact that we're giving it on Zoom, it's also the first time for us. You could already see some glitches today. So things will need adjusting, and please bear with us there. We are doing the best we can, but if you have feedback, that's very useful for us. So if you have any kind of like remarks or things that you see we could improve, please do say so. We'll give you, we'll make an anonymous survey in perhaps 4 or 5 weeks, where you can also give us like some quick feedback about the beginning of the lecture, so that we can try to adapt already during the lecture and take your feedback into account. All right, so that's it for the organization of the lecture. So I hope by now you're all convinced and that you will keep being registered for the lecture, and you will start like playing with us. So here, what I would like to do for the next 15 minutes is actually speak a little bit about P4, because the next exercise that will start at just after the lecture, you will actually implement your first P4 program yourself. So we'll actually look at this together now. I just want to give you the very high level gist about what a P4 program is and what you can do with it, so that you can actually start playing immediately after the lecture. All right, so what we'll do, and again, we won't do everything today. I will clearly not have the time to do that in 15 minutes, but I just want to briefly go through it. It's to look at how we can implement a very basic router in P4. So we'll actually see how we can implement IP forwarding in a traditional router. And we'll do that using P4. So again, P4 is a domain-specific knowledge that enables you to define the forwarding logic of a device. So here, I would like to remember you that in a router, in general, you have a control plane and you have a data plane, okay? So the control plane is the brain that runs the routing protocols that compute the forwarding state that gets downloaded into the data plane. The data plane is usually running in hardware, and it's the part of the router that is responsible for actually forwarding the packets. So the packet enters into the switch performs a lookup according to the forwarding state that has been populated by the control plane, and then the packets get out on the next port. That's kind of like what the router at very high level does. Control plane, data plane. So P4 is about the data plane. So with P4, you program the forwarding logic of your router, not the brain, not the controller. This you can actually use Python, C, whatever you want. Of course, the two, they need to talk to each other, and you will make them talk in the lecture. But what we'll focus on right now is really the data plane aspect of things. So how do you implement forwarding logic? All right, with this said, if you look at the router from a forwarding plane point of view, right? So you only look at the hardware part of the router, and you look at what is the hardware part doing when it receives an IP packet. Like, it doesn't do that much. Of course, it does that very, very quickly because you need to reach terabits per second nowadays. So you only have a few nanoseconds to do all that. But essentially, when the router receives an IP packet in the hardware, it will look up the next step to use. So on which next port do I need to send the packet? It will update the MAC addresses because you're moving from one link to another. So you need to update the link layer addresses accordingly. You will decrement the TTL by 1, and you will drop the packet if it reaches 0. And then you will finally forward the packet to the output port. So this, again, is what a router does in the data plane, okay? Not in the control plane. So the control plane has computed that when packets for that destination arrive on that port, they need to be forwarded on this port, okay? So let's now look at how we can implement these 4 steps in P4 directly. So you need to actually implement each of them in P4. So a P4 program, that's again something you will start to play immediately in the next part of the lecture, in the exercise session, but you will see it's composed of 3 essential parts, 3 fundamental parts. There is a parser, there's a match action pipeline, and then there is a deparser. So these parts, they actually abstract away, if you want, a switch. So when, again, like what a switch does when it receives a packet, it needs to extract headers at the beginning of the packet, like the source address, the source MAC address, the destination MAC address, source IP, dest IP, perform some lookup based on these addresses, and then send the packet out. So the parser essentially is what enables you to do that, to extract the fields from the packet that you care about. And the first important thing in a P4 program. it's simple, and most of the time it will be very similar. But of course, for some perhaps fancy application, you will actually need to change that. And that's where it will become interesting. So parser declares the headers of the IP packet, or like a packet in general, that you want to extract and do something about. Then there is the match action pipeline. So you have your packet arrives, you have extracted the headers, and then you want to perform actions based on these headers. So for instance, as I said, in a router, you need to take the destination IP, and then you need to use the destination IP to figure out where to send the packet next, okay? So that's what you do with the destination IP. The source MAC and the destination MAC, you need to override them. The ETL, you need to decrement them. So essentially, you do that here in this match action pipeline. So it's a pipeline, so we'll have a sequence of stages, and in each stage, you can actually do some operations. And we see how we can put that together. And so the kind of operation, as I said, updating the source address, updating the destination address, decrement the ETL, etc. So something I want to stress, because I understand this is a little bit hard in P4, but is that there is this notion of table in P4. And a table in P4 is a data structure whose content is filled by the control plane, and whose content can be looked up as the packets are flowing through the network. So it's typically, the example here would be an IP forwarding table, which is populated by the control plane, and that you look up as the packets are flowing. So you need to figure out when the packet arrives, right, where to send it. So you need to look up in the table. So in P4, there is a way to define these tables and automatically actually generate the interface with a controller. And that's again something that you will also see and use all the time. I mean, even if it is not super clear now, after one example, I'm sure you will get the intuition. But essentially, this is what is happening here in this match action pipeline. You have a sequence of actions, a sequence of tables you can apply, and then these actions and tables, they're essentially modifying perhaps the headers as they progress through this pipeline. And then at the end of the day, you want the packet to get out, right? You want the packet to be sent to the next device in the network. And so that means that you need to serialize the packet again. You need to put the packet back on the wire. And perhaps you may want to have new headers that have been added as your packet was processed, like a label, like I mentioned in the lecture. So here, this is where the deparser enters into the mix. And that's where you will actually declare how the output packet will look like on the wire. And for instance, you can actually change the way the packet look when it enters and when it leaves by extracting and putting back different fields there. So that's parser and deparser. So really, I want to stress these things again. Like you parse, you extract headers. These headers, they go through a pipeline. In the pipeline, you can do actions. You can look up in tables that are populated by the control plane, and then the packet get out after the deparsing. That's it. So that it's not that complex again, but you, when you are in a network that needs to forward terabits per second, you need to perform this operation in nanoseconds, as I said. So this is what is very challenging also from a hardware design point of view. All right, so like in Java, you kind of have the notion of a main method or main procedure, if you want, in P4. So this is something, again, you will see as you will open your first P4 program, but there will be a main method that put everything together, the parser, the pipeline, and the deparser. That's what is represented here on this slide. So that's your first, perhaps the first time you will see a P4 program, not the last time, I can guarantee you this. And you can see how it looks like. So syntactically, it actually looks a lot like C. So if you know a little bit about C programming, you won't be lost at all. So you have like things like headers and struct, that actually the same in C, includes, same in C as well. And so, of course, the rest will be different because it's a domain-specific language. So it's a language which is targeted to the domain of networks. So here you can see, for instance, there is a first block for the parser, another block for the control logic. So this is the match action pipeline I mentioned, and then the deparser is another control block. So the syntax, you will see, of course, you will see this and you will practice it as you are doing the exercises. It's not that important. You will need to understand it once, and then you will be able to use it for the rest of the lecture and after, of course. So now let me very quickly just give you a little bit of gist about each of the parts so that again, you can do the exercises as efficiently as possible. So the parser, the way it is implemented in P4 and the way you will implement it in P4 is by defining a state machine. So essentially you need to think about your packets entering and the packet that enters a switch, think of it as a sequence of bits. And then essentially what you define is a state machines that tells the switch how to extract headers. So in a sense, sequences of bits in that bit stream that represent, for instance, the source address, the destination address. So you will, for instance, say that the source MAC is defined on 48 bits, and it is immediately after there is a destination MAC. And so, as an example. And so this essentially you do by defining a state machine. And so a state machine has a starting state, and it has an accepting state or a rejecting state. So there are these three basic states that are predefined in P4, start, accept, and reject. And then what you do essentially is you fill in the rest. And so don't look too much on the right-hand side for now, just look on the left-hand side and essentially think about a packet. So when the packet arrives, the beginning of the packet will be the Ethernet header, so the layer 2 header. So essentially you want to parse that first. You want to extract the source MAC, you want to extract the destination MAC. And then in the Ethernet header, there will be a protocol field. And in the protocol field, essentially it will tell you whether the next header is an IPv4 packet or an IPv6 packet. So essentially what you do in defining that state is you define a condition on the transition. If the protocol in the Ethernet header is IPv4, then you actually should transition to the parse IPv4 state. In the parse IPv4 state, you extract source IP, dest IP, etc. And then what is it that you do next? Well, if you want to, for instance, to parse TCP or UDP header, same idea. You need to know whether there is TCP or UDP coming up after. And so you will write a conditional transition based on that value. So that's, now you can look on the right-hand side and you can see that this is kind of like what is going on here in this P4 program. So again, you shouldn't be concerned at all if you don't get everything. As soon as you will start playing a little bit with it, you will see it's actually very intuitive. But essentially, you extract headers from the packet, and then you transition according to some values. And then you define this little state machine. So that's the parser. That's how it works. As I said, in a lot of cases, the parser won't change. So you will be able to reuse that because you will use in a lot of applications the same headers in your application. The match action pipeline, though, this is where a lot of the action actually literally happens, right? This is where you will actually implement the logic really per se of your program. And here, as I said, you can actually put things together. It's a pipeline. So there are multiple stages, and you can define at the pretty low level how these stages are put together. So you define essentially a control flow logic. You can perform actions in these control flows, and you can also look up tables. So as I said, these tables, it's nice because it's a way for you to connect the hardware with the software. So you can essentially ask in your P4 program, you can declare, for instance, that the packet will be forwarded according to some state in the table that has been populated by the control plane. And that's essentially how it works. So the control flow, again, the syntax is not that important now. I really think like the best way to learn about the programming language is by playing with it. And so you will actually play with it very shortly. But essentially what you do in the, as you can see here, what I'm doing in this program is essentially modifying the source MAC address, for instance, with the destination MAC. I'm setting 0x2 as the destination MAC address. I'm decrementing the TTL by 1, and I'm adapting the egress port as well. So that's kind of like, just to give you the idea, but essentially you have like these headers and you can modify them using some instructions. And you can have some variables as well that you can declare. So again, this is something that you need to kind of play a little bit with in order to understand. All right, so it's 3:59. So instead of me trying to go and rush through the table logic right now, I think it's actually best if I stop now, because I think you are well equipped to actually perform the exercises already. So for the exercises, there is another Zoom link that is available on Moodle that you can click on to access the practical exercises session. Normally, you should have received an email with your credentials, and these credentials will enable you to access your very own programmable network environment. So this will be your own little thing that you can program and play with during the semester. If you haven't received that email though, please ping us right now. So send us an email so that we can actually give you the credential right away. So, so that's it for the first lecture. I hope I convince you to actually stick around for the rest of the semester. And I would really invite you to all join the exercise sessions that will start in a few minutes. And please reach out to us if you have any questions or feedback already. I will see you next week, same time, same place. Thanks. I'm also available now if you have questions. So I will stick around a little bit in the Zoom meeting, just in case. So.
Mark, you can go ahead with your question.
Mark, we cannot hear you if you have questions.
Can you hear me now?
Yeah, we can. Yeah.
Thanks. Yeah. So my question was, I was wondering whether there is a reference book for the lecture or a link to a relevant conference venue with papers that might be interesting for us as we're learning about the topic.
Yeah. So there is no, unfortunately, there is no script yet because the materials are kind of like new. So we cannot provide you with a script in advance. There will be, of course, there will be extra reading materials, including papers in conference venues. So we'll mention them. They will be all put on Moodle as we will go along through the topics. But the short answer to your question, there is no syllabus yet. Perhaps next year there will be one, but unfortunately this year we couldn't do a syllabus yet. Yeah. But you have followed ComNet, right? So it's similar. You can expect a similar, let's say, way of proceeding as we do in ComNet. So if that was fine there, it should be fine here as well. Yeah.
Good. Thank you very much.
Yeah, you're welcome. Other questions?
Okay, we have questions about the records and uploads of the lectures. So will the lectures be recorded and uploaded?
Yeah, so good questions. Yes, the lectures will be recorded. I hope they are recorded right now, by the way. And the recording will be put online as soon as possible. Yes. So same thing for the exercise sessions. The sessions will be recorded and made available ASAP. Yeah. Any more questions? Well, then I think we can probably stop now. And so please do reach out though if you have any other questions you may want to ask out of band. It's all fine. And as I said, please connect back now and start playing with P4 and start to see how fun it is to actually play with these networks. So see you all next week, and thanks for attending already.